Hello guys, today we will deal with the sufficient condition of differentiability of function of two variable. So first of all we will prove a theorem which gives us sufficient condition for differentiability of function of two variables. So the theorem's statement is that if f a comma b, if a comma b, sorry, this is if a comma b be a point of domain of function of small f such that these two conditions satisfy. The first condition says that the first order partial derivative with respect to x is continuous at point a comma b, and the second, that is fy, exists at point a comma b. Then we say the given function is differentiable at point a comma b. So we have two conditions. In the first condition we need to show that the given function is continuous. In another condition we will show that the first order partial derivative with respect to y exists at point a comma b. So let's start its proof. So here, since fx is continuous at the origin, at a comma b point, so that means it will exist in certain neighborhood of point a comma b. We take a neighborhood. It is a minus delta, a plus delta. This is the neighborhood of a comma b in form of a rectangular. So a minus delta, a plus delta. This is, suppose, a minus delta, a plus delta, and b minus delta. This is delta distance. This is delta distance. Similarly, b minus delta and b plus delta. And we know that h and k are very small quantities, very small. So a plus h and b plus k is a point which lie inside this neighborhood. Then the del z will be f a plus h b plus k minus f of a comma b, and here we add this factor and subtract it from the above equation. We add the same factor and again we subtract it, so we get this equation. Now we apply the Lagrange mean value theorem, and this theorem says that the f of a plus h b plus k minus f of a comma b plus k, here you can see that the y coordinate is fixed and there is changes in x coordinate by this factor small h. So this will be equal to h partial derivative with respect to x a plus theta h comma b plus k, where theta is a small quantity which is less than 1 and greater than 0, then equal to 0, and it depends on the value of h and k. Again, since fx is continuous at point a comma b, therefore its limit, the limit of fx, will exist when hk tends to 0, and it will be equal to fx a comma b, that is value of function. So we can write it f x a plus theta h b plus k will be equal to f of fx a comma b plus function of hk. This is our equation number 3rd. Now here h and k tends to 0, h comma k, function of hk tends to 0, h comma k tends to 0, 0. Again, since from second condition fy a comma b exists, therefore by definition of fy at a comma b, this will be equal to limit k tends to 0, f a plus a comma b plus k minus f of ab upon h upon k. And we can also rewrite the above equation as, for we remove this limit here and add a function psi k. Okay, so where psi k tends to 0 as k tends to 0. So from here, now from equation first, second, third and fourth, we get that del f is equal to h fx a comma b plus k fy a comma b plus h function of hk plus k function of k. And this tends to 0, this tends to 0 and this also tends to 0. So this implies that f is differentiable at point a comma b. So that means if fx is continuous at a comma b, fy exists at point a comma b, then we say the function f is differentiable. Similarly, we can obtain that the function is differentiable at a comma b if fx exists and fy is continuous at point a comma b. Here is another important note. We have also lots of example where all the partial derivative of function is continuous even though function may not be differentiable, or if none of the partial derivative is continuous even though function may not be differentiable. That means condition of continuity is not a necessary condition for the differentiability of function of a two variable. Continuity of partial derivative is not sufficient condition for the differentiability of function of two variables.